Hello, everybody, and welcome to our next lecture of CHY 113. We're going to start today by looking at a couple of warm-up questions from the material that we covered last time. And so we'll start here with this first one. We talked about classification of matter last time and how we can classify matter according to its chemical makeup, its chemical composition, and the purity of it, really. And so go ahead and take a few minutes and classify these 5 different things as either an elemental substance, a compound, homogeneous mixture, or a heterogeneous mixture. So like I said, go ahead and pause the video now, come back and we'll look at the answers. Okay, and so the first one, soda, we would pretty much, by and large, consider that to be a homogeneous mixture. It is definitely a mixture. There's more than one compound in there, to be sure. And really, it's pretty much uniform. I would honestly accept an argument of heterogeneous mixture due to the carbonation if somebody defended it that way. And so you can see that these can get a little bit gray sometimes, depending on how you look at things a little bit. But really, I would consider for the most part, especially, if you've just poured a soda or you've just opened it and it's sitting there and the carbonation is pretty uniform throughout. So I would consider that homogeneous, but I would see an argument for a heterogeneous mixture there too, depending on how you defended it. A pure gold bar, that's right in the name, pure gold. Only thing in there is gold, and so we only have gold atoms. Gold is one of our elements in the periodic table. See that right here. Elemental symbol Au, and so that's just an elemental substance. No other types of atoms in there. Sucrose, common table sugar. The big hint here is that you're given a chemical formula for it. So this would be a compound. Compounds are made up of more than one type of atom, and they have distinct chemical formulas. Chocolate chip cookie, a delicious example of a heterogeneous mixture. Certainly more than one compound in there, and it's non-uniform. There are definitely differences. You might get one bite loaded with chocolate chips and then another very disappointing bite without many chips in there at all. Or if they were like the ones that my wife just made, some of them might be very nicely done. Some of them might be burned to hell. Don't tell her I said that. And finally, the example of air. So just the air in the room where you are, that would be a homogeneous mixture. There's certainly more than one type of element or compound in there. Air is made up of several different things. A lot of people, well, there's a common misconception sometimes that air is just oxygen, but it certainly isn't. Air is actually mostly nitrogen. The air we breathe is almost 80% nitrogen, and then a little under 20% oxygen. Then there's always some carbon dioxide in there, a little bit of water vapor, some argon is usually in the air. And so lots of different things that make up the components of air, making it a homogeneous mixture or homogeneous mixture. And so next, go ahead and classify these different changes. There are 5 changes there as either a chemical or a physical change. So go ahead and pause the video now, see if you can classify these changes, and then we'll come back and look at the answers. So the first one, solid carbon dioxide sublimes to gaseous carbon dioxide. And so the big hint there, we're going from a solid to a gas. We have carbon dioxide to start with. We still have carbon dioxide in the end, so we haven't made anything new. So that's just a physical change. Sublimation, by the way, if that's not a change that you've heard of before, that's when a substance can actually go directly from a solid phase to a gas phase. Dry ice, if you've heard of dry ice or seen dry ice is nothing more than solid carbon dioxide, and it's called dry ice because at normal atmospheric conditions, it's not going to turn into a liquid at all. So a regular water ice cube, put it out on your desk, it's going to melt into liquid first. Then if you get it hot enough, it'll then escape to the gas phase, but it goes through the 3 typical phases. We go solid, liquid to gas. Carbon dioxide, because of some of its various properties, if you take solid carbon dioxide, put that out on your desk, it's going to sublime directly to the gas phase, but it's still just a physical change. If sodium and chlorine react to form sodium chloride, Then we start with two different things. We're starting with sodium and chlorine. We're ending with sodium chloride, something new. Something new is a hallmark of a chemical change. Same with food digestion. The whole point of food digestion is that the enzymes and bacteria in our digestive system break food down into different molecules, and that's definitely a chemical process. Food coloring turning water blue, that's definitely just a physical change. All we're doing is creating a mixture, essentially. We're mixing two things together, but we're not changing the chemical makeup of anything. It's just a physical change there. Wood burning, absolutely a chemical change. We're making new things and we're destroying some others. And so those are some of the hallmarks of a chemical change. So there, good. A little bit of warm up from last time to get us thinking about what we covered before. And now in today's lecture, we're going to start to focus on some of the math tools that we're going to need in this course. I think I mentioned last time, I really hope I did anyway, that this class is definitely a math intensive course. We're going to approach a lot of different chemical problems in mathematical ways. And chemistry in general is a mathematical science. We generate data, we analyze data, and so we have to know how to work with data and how we work with numbers in a class like this. And so that's really what today's lecture is all about, is looking at some of those tools that we're going to be needing to use all semester long. And so we're going to start by looking at various units of measurement, and that will include a discussion of metric prefixes. We're going to look at different terms called accuracy and precision, which help us to analyze the integrity of our data. We're going to look at scientific notation, which allows us to express very large and very small numbers. We're going to look at something called significant figures, which is a way that we deal with the fact that we're working with measurements and how we work with the number of decimal places that we can really use. And then finally, we're going to look at a problem-solving tool called dimensional analysis, which is something that will really help you in solving some of the various problems that we do in here this semester. And so first, let's just talk about the fact that we are talking about measurements. For the most part, with all of the numbers that we use in this course, these numbers are going to represent the measurement of something. And so a measurement is something that is always going to consist of a number and a unit to go along with it. And you'll excuse me, I will be right back. I'm going to go pause the video. My dog is barking like mad upstairs. So I'm going to go see what's bothering him. Be right back. Teaching remotely. And my cat is now lurking around down here in my office, so I fully expect him to make an appearance in a minute too. So anyway, and so as I was saying, in a class like this, or in chemistry in general, the vast majority of numbers that we encounter represent a measurement of some sort. And so we have to keep in mind that any measurements are going to consist of a number and something for a unit. And the unit is key. The proper units tell us what type of number we're looking at, tell us what the measurement is. There he is. And so we use as you all know, in science, we use the metric system. And so we're going to be using things like meters for any length, grams for measuring mass, seconds for time, and I knew he would pop up soon. And calories, which we'll be talking about later on in the semester when we talk about energy. But just always keep that in mind, that any numbers are going to have associated units to go along with them. It's a little different in this course because all of your work is going to be done on the platform Chem 101, on that online platform. But if this were a live class, one of the things that this would mean for you is that any answers you gave on exams, for instance, would be incorrect if you didn't have the correct units attached. And even with the Chem 101 platform, some of that is taken care of for you, but it is something you're going to have to be mindful even on there, that you'll have to make sure to attach correct units onto any sort of questions you're working with. And in fact, okay, thank you for making an appearance. That was Rangeley, everybody. He's a good kitty. When we talk dimensional analysis later on, dimensional analysis is a problem-solving technique that focuses in on using the units. And so I always make that a big part of the course, and things that we learn about is really talking about the units involved and how we can use those to help us. And these are just some of the various measurements that we will be talking about. I already mentioned some of these, things like length, mass, volume is a measure of how much space something actually occupies. Energy, we'll be working with energy units quite a bit in a few weeks in one of our topics here. In addition, we also have something that we call derived units. Derived units are units that, just like the name says, that are derived from combinations of others. And density is a great example of that. Density is a physical property of a substance, which is a measure of how much mass there is occupied in a certain volume. The typical units of density that we use are grams per milliliter. And so it's how much mass there is, how many grams packed into every milliliter of volume. Density is a real easy calculation. You're going to be doing some work with density and some density calculations as part of your first 114 lab. But density simply equals mass divided by volume. So we find the mass, we find the volume, we divide, and we have the density. And like I said, typically in this class, we will use units of grams per milliliter. And this just gives some nice visual depictions of density. And so I like this one here because it really shows you kind of what we're talking about, that density is a measure of how tightly packed the material is within a certain volume. And so both of these cubes have the same amount of volume, but this one obviously has much more matter packed into it than this one does. And so this is a more dense material than this one. Density also explains why things float. More dense things sink in less dense things. This is why you can have something that for instance, is a huge log. You get some huge log, throw it into water, and it's going to float. As opposed to a tiny little pebble, toss that into water, it's going to sink. The huge log obviously weighs a lot more, but its density is less than that of water. The rock's density is more than that of water, so the rock would sink. And this is an example of what we call a density column. And so you can see various liquids in here that are just separated from each other. We have some maple syrup down here in the bottom. We have a little bit of dish soap then here. A little bit of colored water. You can sort of make out that blue a little bit there. We have some wine here, some vegetable oil, and then some olive oil. You can see that the distinction between those two right about here, or it's right here, I guess. So density columns are made just from pouring in various liquids that are of different densities. And you could even pour them in so that they mixed. And as long as there wasn't anything sort of chemically going on that bound them together, they would eventually separate out into their various densities. Try that sometime, maybe with some oil and water. Or you might have seen it even with something like, especially homemade salad dressings, where you mix some oil and water, maybe some vinegar and water, or vinegar and oil together. Then you let it sit in the fridge. And the reason you have to shake it is because they will actually separate due to their densities. And so this is just a nice, good visual example of that. And this chart just shows us the density of some common materials out there. The density of water at 4 degrees Celsius is 1 gram per milliliter. The density of ice, of solid water at 0 degrees C, is actually a little bit less, 0.917. We'll talk about some of the reasons for that when we talk about intermolecular forces and hydrogen bonding later in the course. But water is actually unique in this. For most substances, the solid form is actually more dense than the liquid form. And so the solid form of most things will sink in the liquid form of it. Not the case with water. Because of some of the different properties of water, ice, solid water, is actually less dense than the liquid form. And so that means that solid water will float on top of liquid water, which is one of the reasons why we can do things like ice fish in the state of Maine. The ice floats. And then there's some other various densities here. You can see things that are gases like air and helium, very, very low densities. Aluminum, lead, gold, some of our heavier metals, very, very high densities. And so if you have, say you had, in one hand, you had 1 milliliter of gold. In another hand, you had 1 milliliter of aluminum. So same volume of each, that 1 milliliter of gold is going to weigh much more. So the same exact volume of aluminum versus gold, the aluminum would weigh much less, different densities, and so forth. Next, we're going to look at metric prefixes. Metric prefixes in general, to me, are one of the big failings of our high school education system. And I say that as somebody who taught high school for a number of years. Yeah, okay. And here's Rangeley again. He loves talking metric prefixes just as much as I do. We'll talk about them later, buddy, okay? You and I will have a good chat about metric prefixes. These are something that I do think should be absolutely just drilled into your heads. And in some high schools, I know they are, others they aren't, but it's nothing that really seems to stick that well a lot of times. And I do think that's one of our failings as a system. So metric prefixes in general are ways that we can express units, express measurements that are much smaller or much larger than our base unit. And so in other words, the base unit of length is 1 meter. If you're not familiar with a meter, so remember a meter stick, you've probably seen a meter stick, about yay long or so. A meter is pretty much just about a yard. There's a little bit of difference there, but they're pretty close to each other. So 1 meter is approximately equal to a yard. But let's say now that I'm talking about a measurement that is tens of thousands of meters. Well, it's more convenient for me now to think in terms of kilometers, where a kilo, 1 kilometer, 1 kilometer is equal to 1,000 meters. Likewise, if I'm thinking about something that's really, really small, if I'm thinking about something that is on the scale maybe of the size of an atom, now we're starting to get down to 0 point, and then 10 zeros, 1 meter. Not real convenient for me to think in terms of meters there, but it is convenient for me to think in terms of picometers, which we'll see what that is in just a minute. And so that's what metric prefixes allow us to do, is attach a prefix, which is something that stands for a much smaller or much larger measurement than the actual base unit that we're talking about. And these are the main metric prefixes that we're going to use in this class. And we need to know how to convert these. This is something that you are just going to have to memorize and be able to do and be able to convert between these. The vast majority of these are ones that you will need to be familiar with. I would say don't really worry necessarily actually about pico or femto. We don't use those a whole lot. But the rest of these, from nano on up, absolutely, you're going to need to know how to use these and how to convert these. I'll talk about how we use the prefixes a little bit here. But again, remember all of the different supplemental materials that are available to you. You can get a lot more help with metric prefixes if you go to Unit 1 here on the website, and then to Unit 1 materials. You'll see a couple different resources. One of those is a supplemental video that will go deeper into what I'm about to talk about and in a little bit more detail. You'll also see some good practice on metric conversions that walk you through some of the processes in even a little bit more detail that will help you out. So don't forget that those resources are available to you as well as what I'm about to talk about here. And so generally with metric prefixes, and so we would consider sort of this line right here, in between deci and kilo, this is where our base unit would live. Now metric prefixes can be used with absolutely any sort of measurement. You can put a metric prefix in front of meters, you can put it in front of grams, you can put it in front of liters, tons, hertz, which is a measurement of frequency that we'll talk about later in the course. So any unit that you can think of, you can put a metric prefix in front of it. And so if this is sort of our baseline right here, anything above this line, kilo, mega, and giga, these represent measurements that are larger than our base unit. And so 1 kilometer or 1 we'll use this example here. 1 kilogram represents 1,000 grams. Mega represents 1,000,000 of that unit. So 1 megaton is 1,000,000 tons, or 1 times 10 to the 6th. You can see that 10 to the 6th right here. Giga is 1,000,000,000 of the base unit. And so 1 gigahertz is 1,000,000,000 hertz, or 1 times 10 to the 9th hertz. Anything below this line, now we're getting to measurements that are smaller than our base unit. And so a decimeter is 1/10 of a meter. A centimeter is 1/100th of a meter. With that one, think in terms of, okay, thank you, buddy. Think in terms of things that you know. 1 penny, 1 cent is 1/100th of a dollar. Same idea, that's where it comes from. A milli is 1/1000th, so a millimeter is 1/1000th of a meter. A millisecond would be 1/1000th of a second, so forth. Micro is 1/1,000,000th of something, so a micrometer is 10 to the negative 6th, or 1/1,000,000th of a meter, and so forth. A nanometer is 1/10000000th of a meter, 1 times 10 to the negative 9th. Now, there are different ways that you can go about doing these conversions. Let's just pull up our whiteboard here. Let's say, for instance, because you're going to have to do these metric conversions for numbers of different reasons. Quite often, for instance, you might be given a measurement maybe in terms of meters, and you need to convert that to nanometers for something that you're working with, or the other way around. You might be given a measurement in terms of nanometers, and you need to convert it to meters in order to use it in an equation that we have. Most equations that we have are very specific about what type of unit you can actually put in there. However, it's more convenient for us to report measurements, sometimes using our metric prefixes. And actually, the example I just used is a great one. If we're talking about the frequency of, the wavelength of certain types of light, and this is something that we'll talk about that topic later on, so don't worry about that. But it's real convenient for us, or it's more convenient to discuss wavelengths in terms of nanometers. And so if I tell you that we're working with a certain wavelength of light that is 450 nanometers, well, that's great. That's how we report it. That's 450 nanometers for a wavelength. But to use it in an equation that we're going to see later in the course, we have to convert that over to meters. And so what I would do, so we have to recognize that our decimal point is right there. And so there's a couple ways to go about it. One thing that you can do is recognize our exponent right here. And it might be tough to see that on your screen just because I reduced the size a little bit. But a nanometer is 1/10000000th of a meter, or 10 to the negative 9th. And so what we can do is say, okay, well, that negative 9 means we have to move our decimal point by 9 spaces. We also know that we're going from our base unit to a smaller unit, we're going from nano to our base unit. We're going the other direction. So we're going from nano to our base unit. So we're going from a smaller number to a larger one. That means that our number is going to get smaller. That can be a little counterintuitive, but again, think of it in terms of something that you know. If you're converting 150 cents over to dollars, it would be the same idea. You're going from cents up to your base unit. So you're going from a smaller unit to a larger one. And so if we're going from cents to dollars, our number is going to get smaller. So same thing here. We're going from nano to our base unit. And the 9 in nano tells us that we're going to move our decimal point 9 spaces. So if our number has to get smaller, then we're going to move our decimal point to the left by 9 spaces. So we're going to go 1, 2, 3. And this is literally what I still do sometimes when I do these conversions on paper. I've gone 3, so I need to go 6 more. I make little humps. 4, 5, 6, 7, 8, 9, running out of space. But there's my decimal, my new decimal point there. And so then these are all going to be zeros in here. So let's count that. I now have 1. Where's my little pointer? Oh, sorry, there we go. 1, 2, 3, 4, 5, 6 zeros now in front of my actual number. And so this then would convert out to 0.12345 meters. Just like that. Let's say I'm going the other direction. Let's say that I need to convert, if I have a certain amount of wattage, maybe I'm talking about electricity, and I need to convert 45 million watts over to gigawatts. So same thing. Now I'm starting here at my base unit, or we'll say to megawatts. We'll make that a little bit easier. We're going to convert to megawatts, or just to do a different number. And so I'm starting here. Mouse is touchy. I'm starting here at my base unit, and I'm going to mega. The exponent for mega is 6. So that tells me I'm going to move 6 decimal places. My decimal point starting right here. So I'm going to move 6 decimal places. I'm going from my base unit to a larger unit, so my number is going to get smaller. And so again, I'm going to move my decimal point to the left. 1, 2, 3, 4, 5, 6 equals 450 megawatts, and so forth. And so that's how we do metric conversions. When we talk about dimensional analysis in a little bit, you'll see that you can also perform metric conversions using different dimensional analysis techniques by simply using some unit conversion methods, which we'll look at and see. But again, for some more help with these, definitely watch that other more in-depth video and look at some of those practice problems. I think those will help you out too. Scientific notation is another way that we use to express very, very large or very, very small numbers. And so, for instance, if we're looking at the distance to the sun in miles, it's 93 million miles. It's more convenient for us sometimes to express that in a different way. And so scientific notation is always expressed in powers of 10. And it's going to be with a number in the ones spot, point whatever the rest of it is, and then times 10 to whatever exponent. And so in the case of the distance to the sun, our decimal point would be starting here. If we're looking to convert this to a scientific notation, our decimal point starts here. So in order to get our decimal point here for the 9 in the ones spot, we have to move it 1, 2, 3, 4, 5, 6, 7 spaces. And so we're moving it to the left, which will give us a positive exponent. So we get 9.3 times 10 to the 7th miles. The radius of a carbon atom, this is frustrating me. Here we go, is 0.00000000070 meters. So a couple different ways that I could go about this. I could either use a metric prefix. In this case, it would be convenient for me to maybe use micrometers. But again, maybe I have an equation where I need to leave this in meters for whatever reason. So it might be convenient for me to now move this to scientific notation. And so in order to get this into the form of scientific notation, I'm going to need to put my decimal point right here after the 7. Which means I would have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spaces. And I'm moving it now 11 spaces to the right, which means I would get a negative number. So I get 7.0 times 10 to the negative 11. And so this gives us a much easier way to represent very, very large or very, very small numbers. Now, one thing you have to be very careful of is when you're using scientific notation with a calculator. This is the reason why we need a scientific calculator for this course. Scientific calculators are built to use scientific notation. So the way that you will use scientific notation in your calculator, and this is very, very important, and it doesn't matter how much I stress this, I guarantee that some of you are going to come to me at some point in a few weeks and say, I'm not getting right answers. What am I doing wrong? We're going to look at your calculator, and it's going to be because you're putting them wrong into your calculator. And so please pay attention when I tell you how to do this, because it is important to get right answers with your calculator. you have to use, and this will be a different button depending on your calculator, but with most calculators, it's EE, either lowercase or uppercase. Sometimes it's EXP. Sometimes you'll see, thank you, yes, Rangeley likes scientific notation too. Sometimes you'll see a times 10 to the n or a times 10 to the x. This takes the place of the times 10 exponent. And so in other words, if you have the number 5.65 times 10 to the fourth, so that's a number expressed in scientific notation, in order to put that into your calculator, it's going to be 5.65 EE4. And that's it. That's how it goes in. You don't put the 10 in, you don't put the little caret for your exponent, none of that, no multiplication symbol. That EE tells the calculator that it is scientific notation. Now, again, that button might be different depending on the type of calculator you're using. If you're using something like a TI graphing calculator, then it's moved on some of them, but you're looking for, in this case, for the TI-84, for instance, it's above the comma button. You have to use the second and then comma. So in this type of calculator, I would literally go 5, raise it up there so you can see it, 5.65 second EE4. And then I would put it in just like that. And you can see how it's actually displayed on the calculator, 5.65 E4. And so that puts it in as scientific notation. You can see it as well. If you're using this type of calculator on the computer, there it is as the EE. Don't get it confused with this E, which is a very different mathematical function. If it's E's on your calculators, it'll always be 2 of them. Again, it would be 5.65 E4. And if you hit equals, then it just does it out for you. But you don't have to do that. You could put in your calculation just like that, 5.65 E4 times whatever you're trying to do, blah, 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 and then it would do it out for you. But that is very key, especially in instances where maybe the number that you're doing in scientific notation is in the denominator of a problem, because your calculator is very strictly going to follow order of operations. And so it's going to become very important for you to put numbers into your calculator in a way that the calculator will recognize that you're trying to do some scientific notation in there. And so always get used to using that EE button. Okay, next we're going to talk about ideas known as precision and accuracy. Precision and accuracy are ways that we can evaluate sort of the integrity of our data. We always try, and you'll see this in lab, we always try as much as we can to take multiple measurements on any data that we take. And then we have to look at trying to figure out, well, how much can we actually trust that data? So precision will tell us how close all the measurements actually are to each other. They don't tell us precision doesn't tell us if we're close to what the actual number is. That's what accuracy does. Precision tells us amongst that data set that we took, how close are all the measurements simply to each other. Whereas, like I said, accuracy will then tell us how close the average of all of those measurements are to the actual true value. And so, for instance, here we have a set of 3 different measurements of the mass of a 7.5-pound infant. And we took 4 different balances. Yeah, so these are the 4 different balances, and each had 3 different mass measurements taken. And so we can see, for instance, in this one, in the first one, we had a mass measurement of 7.5, 7.6, and 7.4. So that all averages out to 7.5, so pretty accurate. And all of the measurements we can see are really close to each other, 7.5, 7.6, 7.4, all really close to each other. So it's also a precise data set. This data set here, all our measurements are pretty precise. They're all close to each other, but the average isn't close to the true average. So this is precise, but it's not accurate. Here, we have measurements that are sort of all over the place. So they're not precise, but they average out pretty close, or right on, actually. They average out very accurate, but the measurements are all over the place and not precise. Here, we have a set of measurements that is neither precise or accurate. The average isn't close to the true average, and the measurements are all over the place. Accuracy and precision in general is something that you'll be looking at a fair amount in lab. In 114, you will be doing several statistical exercises for most of the data sets that you take to try to determine both their precision and their accuracy. Which now brings us to something we call significant figures. And so, as I mentioned before, we have to keep in mind that all of the numbers that we generate in a class like this, or all the numbers that we work with, are representative of a measurement. And a measurement is only going to be as accurate as the measuring device we're using allows it to be. And so, for example, here, we have two separate measurements of, it looks like maybe some copper sulfate in here. We have a balance here, we have a scale that allows us to measure to the 10th spot. However, this balance here actually allows us to carry that measurement out to the 100,000th spot, to 4 decimal places instead of 1. And so this one allows us to measure our mass much more accurately than this measuring device does. And so we take that into account into something that we call significant digits, or significant figures. Because our final measurement that we give, if we're doing, for instance, if we're working with some sort of calculation maybe of density, our final density calculation, our final grams per milliliter that we calculate, can only be represented as accurately as our least accurate measuring device. And so we have to take what we call these significant figures into account. And we'll look at these rules in a minute, but this would be a measurement that has 3 significant figures versus this measurement that actually has 5 significant figures. And so we would have to take that number of significant figures into account if we were doing a density calculation with this particular measurement. So let's take a look at what I mean with an example here. And so let's say again that we're trying to find the density of something, and we know the volume to be 10.1 milliliters, but then we put this our item on a balance, and our balance maybe only measures to the 10th spot, and we get a value of 12.3 grams. And we have 10.1 milliliters. We put this into our calculator, and we get 1.2178 grams per milliliter. So our calculator is going to spit all these numbers out to us. But remember that a measurement is only as good as the accuracy of the measuring device. This is a balance. We're not going to worry about the volume for this, but thinking about the volume would even compound the problem I'm about to talk about. If we just consider the mass for a minute. So this is a balance that can only measure to the 10th spot. It reported a mass of 12.3 to us, but that means the reality is that this mass was somewhere between 12.25 grams and 12.34 grams. Any mass within that range, this particular balance can only report as 12.3. And so let's say that the mass was actually closer to the 12.5. So again, the 12.25, that would have returned 12.3 to the balance. But if it was actually 12.25 grams divided by our 10.1 milliliters, then that would give us a number of 1.21287127 grams per milliliter. And likewise, if it were closer to the upper end, if it was 12, hopefully I've got an undo function on here, 12.34 grams divided by 10.1 milliliters, then I get 1.22178178 grams per milliliter. And so realistically, the density of this object is somewhere in between these two numbers. And I don't know where it is in there because the accuracy of my measuring device that I use for mass only allows me to go to the 10th spot. And so I know that my actual density is somewhere in between these two. And so that means that it's really unfair for me to report. I can't report this number because I don't know the density that accurately. I don't know it because of the limitations of my measuring device. And so what we do, and we're going to look at the rules for significant figures in just a moment, but we round our final answer to reflect the least number of significant figures in our measurements. In this case, our least number of significant figures is 3. So we're going to round our answer to 3 significant figures. So we would report an answer of 1.22 grams per milliliter. And that is how we would take our significant figures into account. This would be your answer, taking into account the significant figures of our least accurate measurement. And so how do we determine the number of significant figures then? We use these rules here. And so what you have to do is count up in your measurements, count up how many significant digits or significant figures there are in each measurement. When you're doing that, actual numbers, those are easy. If it's a real number, if it's a non-zero number, that is significant. And so 3.45. There are 1, 2, 3 digits there that are all non-zeros. This measurement has 3 significant figures. Zeros are where it starts to get a little bit tricky and we have to think about some rules. With zeros, we have what we call placeholder zeros, or zeros that are actually part of the measurement itself. And so if you have a 0 that is between 2 non-zero digits, then that 0 is significant as part of the measurement. So something like 3.05. This 0 here is between 2 others that are non-zeros. And so that 0 counts, it is significant. If you have a 0 that follows a non-zero digit, which is to the right of the decimal point, that is significant. A 0 before the decimal point may or may not be. But if you have a 0 to the right of the decimal point, following a non-zero, that's the key. If it's following a non-zero after the decimal point, that is significant. And so in this case, 0.400, these 2 zeros here, or this 0 here and 4.0, those are significant. And we have to count them when we're counting our significant digits. And if we had an answer that we had to report that many significant digits, we would include these zeros. Now it's true, mathematically, those zeros don't count. But we have to remember again that our numbers represent measurements. And there is an absolute difference between this number here, maybe 0.41 grams versus 0.410 grams. Mathematically, sure, those are equal to each other. Measurement-wise, they are absolutely not. Measurement-wise, I have a number here that I know to 1 greater decimal point compared to what I know this number. This is a much more accurate number. The balance that reported this number to me probably cost $1,000 more than what the balance did that gave me this number, or maybe more than that, a few thousand more. And so this 0 is significant. It is a 0 following non-zero digits after the decimal point. And so one of the things to ask yourself is this 0 something that lends itself to giving me more information about the accuracy of my device? And this one does. This one tells us that we know this measurement more accurately. And so that's a 0 that would be significant. If there's no decimal point at all, then zeros following a non-zero digit are not significant. They're simply placeholder digits. And so what I mean by placeholder is, like in this case here, 6,000. These zeros here are not significant. They're merely telling us that our actual measurement starts in the thousands spot. So our actual measuring starts here. And so those zeros are not significant. We would say that this number only has one significant digit. Now, if I put a decimal point right there, though, that's telling me that those zeros now are significant, that I have measured this measurement accurately to the ones spot. And that's the other way to think of it, is that these three zeros in this case simply tell us that we've only measured this accurately to the thousands spot. This decimal point here tells me that I've actually measured accurately to the ones spot. So now those zeros are significant. Zeros that appear before non-zero digits, whether or not there is a decimal point, are not significant. In other words, this here. These three zeros here are also just placeholders. They're telling me that my measurements start in the 100,000th spot, here in the fourth decimal place. So these are simply placeholder zeros here, but this zero does count. This zero would follow our rules up here, that it's a zero following a non-zero to the right of the decimal point. So we would have two significant figures here. Then finally, our last one. Anytime we're expressing numbers in scientific notation, all of those zeros are significant. That's the other nice thing about scientific notation, is they remove any ambiguity that we might have due to significant figures. We know that since this is expressed in scientific notation, that those zeros are absolutely significant. And so significant figures in general can be one of the more difficult things sometimes for students to wrap their heads around. So spend some time with this. This is another area where some of these supplemental videos might help you out. I'm pretty sure I do. Yes, here I do. I do have a video on significant figures here. I have some significant figures practice with the key right on the website. So absolutely spend some time with those. Work with it a little bit, because significant figures are not always the most intuitive concept for students to understand. And so really work with some of the materials on that to see if that helps you out. Significant figures in general represent measurements. We do have to recognize that there is a difference between measurements versus a counted number. Counted numbers are considered to be exact. There is no uncertainty there, and therefore we would consider them to have an infinite number of significant figures. For instance, the number of students that are enrolled in this course, as of the time right now that I'm doing this lecture, I believe it is 86 students total. And so that 86 is an exact number, and has infinite number of significant figures. And so I would not, any calculation that I was doing with that, for instance, if I was calculating an average, I wouldn't have to consider the number of students in my significant figure reasoning, because there are an infinite number of significant figures in the number 86 when it's like a counted number like that. Now, when you're doing calculations, and so dealing with sig figs and calculations, when you're multiplying or dividing, it's actually pretty simple. Your final answer simply cannot have more significant figures than the measurement with the fewest number of significant figures. I know that sounds complicated, but it really isn't. So for instance, when we were looking at the density earlier, if I have maybe 3.26 grams divided by 4 milliliters, then I put that into my calculator, and I get 3.26 divided by 4. My calculator is going to give me 0.815 grams per milliliter. But I look at my significant figures, I have 1, 2, 3 here, I have 1 here. My final answer can only have the number of significant figures as my least accurate measurement. My least accurate measurement has 1 significant figure. And therefore my answer, I have to round to 1 significant figure. So I'm going to report this as 0.8 grams per milliliter. And just use standard rounding rules. I forget if it's this book or another one, did some funky things when it came to rounding with the number 5. I'm not going to worry about that. Use the rounding rules that you learned back when in second grade when you were 7 years old. 5 and above, round up. below 5, round down. Just use standard rounding rules. But let's say instead, maybe this was 3.26 divided by, maybe I measured my volume more accurately, 4.3 milliliters. Now I'm going to have 3.26 divided by my 4.3. I put that into my calculator, and I get 0.7581395 and a few more digits. But I count up my significant figures. I have 1, 2, 3. I have 1, 2. So now I can round to 2 significant figures. So I'm going to have 0.76 grams per milliliter. So that's how you would use significant figures when you're multiplying or dividing. Adding and subtracting is a little bit different. When you're adding and subtracting, you don't look for the actual number of significant figures. You look for the measurement that took you to the fewest places past the decimal point, and you cut your final answer off there. And so, for instance, let's say I'm just adding up a series of numbers, could be for anything. Maybe it's lengths. I'm adding up some various lengths. So I have 4.2, these are all in meters. 4.26 meters, 12.178 meters, and something else that's 4.1. So I add those all up. See how good my addition is here. I get 8, 13, 1, 3, 4, 5, 2, 8, 10. I get 20. My decimal point's right here. But if I look at where the measurement that goes to the fewest places past the decimal point, here I go 2 places past, I go 3, I only go 1 here. So my answer has to be cut off at 1 decimal point. So I have to cut my answer off right here. Again, standard rounding rules. It's a 3 after this. So I'm going to go ahead and just keep it rounded down. And so I'd round my answer then to 20.5 total meters. Maybe this is the perimeter of a triangle, something like that. And so that's how we would do adding and subtracting. You won't see this often, but if you happen to have a calculation that's a little more complicated or you have to do both, then you would apply the set of rules sort of as you go. If you have, for instance, addition and subtraction within parentheses that you have to do, you're going to do that addition and subtraction, apply your Sig Fig rules to that, and then use that number maybe in your multiplication and division. So you would go about it that way. The last thing to talk about today is something called dimensional analysis. Dimensional analysis is a problem-solving tool which allows us to use the units to show us how to set up a problem and cancel things out. And so actually, rather than going through these slides here, there's only a couple left anyway. Let's look at an example. And so dimensional analysis in general is something that you all know how to do. You just don't necessarily know that you know how to do it. And so a great example of this is if we're trying to calculate the number of seconds that somebody has been alive. And so let's start with me. And this actually is one of those things that's more fun live because I always love to ask the question, how old do you think I am? And I love watching people's faces. I get the suck-ups who try to tell me, oh, you look 26. And I get the people who are clearly going to fail my class who tell me that I look 57. So this is always a little bit more fun live, but go ahead, throw some guesses out there, just sort of in your head, whatever, how old do you think I am? All right, I'm 44. So 44 years old. As my wife so kindly pointed out, I will be 45 in June. Doesn't seem possible, but 44 years old. And so if we're going to figure out how old I am in seconds, again, that's something that you all know how to do. And so let's discount leap years. Let's not even worry about leap years for a second because they're just going to throw us off. Let's forget leap years exist for just a minute. And so the first thing that I would do is I would take my 44 years, and I would multiply that by 365, right? 365 days per year. And so let's do that. 44 years times 365 days per year. The next thing you're going to do is multiply by 24 hours in your day. So 24 hours in a day, okay? We would step that now down to minutes. And so we would go 60 minutes per 1 hour, and then finally to seconds, 60 seconds per 1 minute, for an answer of, and this is always painful because it's a big number. Oh, it looks like my calculator finally died on me, so I will instead do it out right here. We have 44 times 365 times, times 24 times 60 times 60. We get, oh boy, 1,387, 84. So 1,387,584,000 seconds, give or take. That's a lot. But that's dimensional analysis. You all know how to do this. Every single one of you out there could have done this problem. What you did, without realizing it, is you use what we call conversion factors. Each of these are conversion factors which allow us to convert in between units. We use this one here to convert in between days and years. We know that there are 365 days per year, so we can use this conversion factor. The power of conversion factors, and where you can start to use dimensional analysis to help you solve problems, is that conversion factors can be written either way. I could either write, just as I did in this problem, 365 days per year for 1 year, or 1 year per 365 days. Either way is absolutely fine. And so the way that I wrote that would depend on what I'm trying to solve. If I want to find, if I have the number of years, if I know, for instance, 3 years, and I'm trying to find the number of days, then I'm going to use the first way I have this written, 365 days per year. And if we see what happens, let's forget about the numbers and just look at the units of this for a second. What I'm doing now is I'm multiplying years times days, and then I'm dividing by years. Look at what happens algebraically. Years divided by years cancels out, and I'm left with days. And that's perfect. That's what I wanted to do. I had said that I'm trying to calculate the number of days in a given amount of years. So it worked out perfectly. And if I wanted to go the other direction, let's say I knew that I had 3,672 days, and I want to know how many years that is, then I'm going to say in 1 year, there's 365 days. And so then I would take, and so then when you set up a dimensional analysis problem, everything up top then gets divided by everything down bottom. And so in this case, I would then do that out. Didn't mean to open up my messages. I would do that out to get 3,672 divided by my 365. I'll look at my significant digits. This is another good significant digit example. So 3,672, this conversion factor here, this is an exact number because there are definitely exactly 365 days per 1 calendar year. And so this has infinite significant figures. And so I'm going to use this to determine my number of significant figures, 1, 2, 3, 4, 1, 2, 3, 4, so 10.06. So in 3,672 days, that's the span of 10.06 years. And so what dimensional analysis really allows you to do is you don't have to necessarily think about, well, do I multiply or divide? What do I do here? How do I set this up? Let the units tell you how to set it up. You always want to set your conversion factor up so that the thing that you need to cancel out is going to be opposite. One up top, one down bottom. And then you're left with what you're looking for in the spot that you're looking for it. And so let's look at an example. Let's say that we know a speed of something that is traveling 25 miles per hour. And we want to just do something simple at first. We want to maybe convert that to yards per hour for whatever, we can go even easier. We'll go feet per hour, right? We want to convert this now to feet per hour. We know that there are 5,280 feet per 1 mile. The question is, do we set up our conversion factor like this or like this? And so we can see that we need miles to cancel out, and we want to be left with feet up top. So I'm going to set my conversion factor up like this. So that then miles cancel out, and I'm going to be left with feet. So would then do 25 times 5,280. 25 is our measurement, so we have to round that off to 130,000 feet per hour. And so those are simple examples, but that's how dimensional analysis works, and that's the beauty of dimensional analysis. It will allow you, it will show you how to set problems up, even if you don't necessarily know what's going on. And I always hate to put things like that, but it's true. You might not understand the science and the chemistry of what we're doing at certain times. That's almost guaranteed to happen. But if you pay attention to your units, you can use dimensional analysis to help you get right answers. It's a very, very powerful problem-solving tool. Okay, I paused the video real quick so I could bring up Chem 101 for a minute, because there are some dimensional analysis setups in Chem 101. I just wanted to show you how those work. So this is one of the things that I do like about this platform, is it helps drive you through dimensional analysis and shows you some of the steps of dimensional analysis. And so let's take a look at this problem here. We are looking to convert 34 millimeters to inches. And so the way that you want to use the dimensional analysis setups in Chem 101 is you drag your starting amounts into this starting amount here. What I would do then is, if you click on here to equal your answer, I would then drag your answer that you're looking for down here. It just helps you keep your eye on the ball, so to speak, and see what it is that you're looking for and what you want to convert. The next thing you have to figure out is what conversion factors I have, or what conversion factors I might be able to find that will help me get from one to the other. Now, these are some that you might have to look up a little bit, either in your book or use some various resources. But one of the conversion factors that I happen to know is that there are 2.54 centimeters per 1 inch. So that's something that might be able to help me out. And so if I can find a way to get to centimeters, then I'm going to be able to then get to inches using that conversion factor. So I have to first then maybe think about getting from millimeters over to centimeters. And so what I might do is go from millimeters to my base unit. That might make things a little bit easier. So I want to go from millimeters to meters. So I'm going to put millimeters down here. And we can see that cancels out. Chem 101 shows us that that'll cancel. But I'm going to put meters up top. And I know that there are 1,000 millimeters per 1 meter. That just comes from our metric conversions that we had talked about earlier. And so now, if I stop the problem, I'd be at meters. That doesn't help me out. I need to add in another conversion factor. Now I want to go over to centimeters. And so I want to go to centimeters. So I'm going to drag that in. I want meters to cancel out. I know that there are 100 centimeters per 1 meter. Now we're getting somewhere. Now we're at centimeters. I'd mentioned before that I know the conversion factor between centimeters and inches. I'm going to drag centimeters down here, so that'll cancel out. Drag my inches. get my 2.54, that is 2.54 centimeters per 1 inch. And then Chem 101 sort of walks you all through it down here. And so then we would put that into our calculator. I keep forgetting mine, my TI is dead. And so everything up top gets divided by everything down bottom. We can use parentheses here to help us out. So everything up top, we have 34. I sometimes include the ones just to sort of help me as I walk through it, help me keep things straight. 34 times 1 times 100 times 1 divided by, now I want to use parentheses for everything down bottom. So I'm going to start a parenthesis here. 1,000 times 1 times 2.54. Close my parentheses, so that's everything down bottom, equals 1.338, blah, blah, blah. I look at my significant figures, 1, 2, 3 significant figures here in my initial measurement. My answer can have 3 significant figures. I'm going to round this then to 1.34, which luckily is one of my options. Let's see if that is correct. And there it is. 1.34 inches. So that's how you would set up dimensional analysis within Chem 101. Now, not necessarily real intuitive. Play with it a little bit as you're doing some of your homework. Play with your setups here and try to use that to help you out. As always, so on the website, there is some dimensional analysis extra practice. There's a nice handout here, actually, that talks about dimensional analysis, what it is, how we use it. And I'm pretty sure, yep, that there is also an extra video on dimensional analysis as well. So lots of tools that can help you out. And that brings us to the end for today. And so this then, what we've looked at are a lot of the different mathematical tools that we are going to use throughout this whole semester. And so these are important to master. These are things that we're going to be using all semester long. So this is a pretty important topic. And so as always, if you have any questions, be sure to talk to me. And also remember that there are tutors available at the Learning Commons that should be starting up their hours pretty soon if they haven't already. That is an incredible resource that I would also encourage you to use. And so until next time, I hope everybody has a great day.